1,000 miles per hour. That is how fast you are moving. Right now, sitting in your chair, thinking you are perfectly still, feeling nothing at all. You are on a rock that is spinning so fast that the surface at the equator is whipping around at about 1,000 miles per hour. That is faster than the speed of sound. It is faster than a bullet leaving a rifle barrel. You are going supersonic right this moment, and you do not feel a thing. That should bother you. Go outside, stand on the sidewalk, hold your arms out, feel the air around you, still, quiet, maybe a faint breeze from the west, but nothing that suggests you are riding a giant ball screaming through space. Your coffee sits flat on the table, smoke drifts straight up from a chimney, a soap bubble floats lazily in the sun, a spider hangs on its thread without being flung sideways. Everything around you, everything you can see and touch and measure, behaves as if the earth is absolutely, completely dead still. So either all the astronomers are pulling your leg, or something about the way you think about motion is deeply, fundamentally broken. I am going to show you it is the second one. Your gut feeling about what it means to move has a crack in it, a beautiful crack. And once I show it to you, you will never look at a car, a plane, a cup of coffee, or the night sky the same way again. But first I want to make the problem worse. I want you to feel it in your stomach, because I do not think you appreciate yet just how absurd this situation is. The Earth is roughly 25,000 miles around at the equator. It makes one complete rotation every 24 hours. Do the division, about 1,038 miles per hour. That is the spin velocity at the equator. A little less up north, a little less down south, but at the equator, just over 1,000. You know what goes 1,000 miles per hour? A .45 caliber rifle bullet. Just about that speed coming out of the barrel. You are at this very moment moving through space as fast as a bullet, and you cannot feel it. But do this instead. Get in your car. Roll down the windows. Go 60 miles per hour on the highway. The wind is deafening. Your hair is whipping around. Bugs are hitting the windshield. Your eyes are watering. That is 60. Now multiply that by 17. 17 times the wind, 17 times the force, 17 times the violence of air slamming into your face. That is 1,000 miles per hour. That is how fast the surface of the earth is going. The air should be tearing the skin off your face. It should be ripping buildings out of the ground. The oceans should be sloshing off the planet like water off a spinning basketball. And none of it happens. But we are not done with the terrifying numbers. The spin is just the appetizer. The Earth is also orbiting the Sun at about 67,000 miles per hour. The solar system is wheeling around the Milky Way at 500,000. And the galaxy itself is plowing through the cosmos at over 1,000,000 miles per hour. Add it up, you are moving at over 1,000,000 miles per hour through the universe. Right now. And your coffee is not even rippling. So the question is not just why can't I feel the Earth spin? The question is much bigger. Why can I not feel any of this? Not the orbit, not the galactic drift, not the cosmic velocity, not even the spin. What is nature hiding from me? Why is the ride so perfectly, impossibly smooth? That is what I want to crack open for you. And the answer is one of the most profound things in all of physics. We need to go back about 400 years to a man who asked this exact question and came up with an answer so good that it held up for 3 centuries, until Einstein came along and only made it stronger. Galileo Galilei. Around 1632, Galileo published a book called Dialogue concerning the 2 chief world systems. This was the book that got him in trouble with the church because it argued that the earth moves around the sun. But buried inside it is a thought experiment that I believe is one of the 10 most important ideas in the history of science. And it has nothing to do with telescopes or planets. It has to do with a boat. Galileo says this: imagine you are below deck on a large sailing ship. The ship is moving across a calm sea at a constant speed. You are locked in the cabin. The portholes are closed. You cannot see outside. You cannot hear the waves. You have no information about whether the ship is gliding forward at 10 knots or tied up quietly at the dock. Now inside this cabin, you have set up a little laboratory. You have a glass bowl full of fish. You have some butterflies fluttering around the room. You have mounted a bottle up near the ceiling that is slowly dripping water into a jar on the floor directly below it. And you have a friend standing across the room, and the 2 of you are tossing a ball back and forth. Galileo asks one question: can you tell if the ship is moving? Start with the fish. If the ship is moving forward, do the fish have to swim harder to keep up with the front of the bowl? Does the water inside the bowl slosh toward the back? Do the fish clump together at one end? Galileo says no. They swim with equal ease in every direction, exactly as they would if the ship were motionless. Same with the butterflies. They do not pile up against the back wall. They fly freely in every direction. Same with the ball you toss to your friend across the room. You do not need to throw harder toward the back of the ship. The throws feel identical in every direction. But here is the sneaky one. The dripping water. The ship is moving forward. A drop leaves the bottle and falls. While it is in the air, the ship moves forward. The jar should slide out from under the drop. The water should splash on the floor behind the jar. That is what your gut tells you. But Galileo says, no, every single drop lands in the jar, dead center, perfect aim, the same as if the ship were at anchor. Galileo's conclusion lands like a thunderclap. He says, shut yourself up in the cabin, perform any experiment you like, and you will not discover by any means whatsoever whether the ship is moving or at rest. Not a subtle hint, not a tiny asymmetry, nothing. The physics inside that cabin is perfectly, absolutely, exactly the same, whether the ship sails or sits still. Why? Because the motion of the ship is common to everything inside it. That is the magic word. Common, shared. The air in the cabin is already moving at the ship's speed. The drops of water are already moving at the ship's speed. The fish, the butterflies, your friend, the ball, every molecule of everything in that room already possesses the ship's velocity before any experiment begins. When the drop leaves the bottle, it does not start from rest and fall straight down while the jar races away. No, the drop leaves the bottle already moving forward at the ship's speed, so it falls downward and moves forward at the same rate as the jar, and lands right inside it. The forward motion is shared, and shared motion cancels out of every observation. That is the principle of Galilean relativity, and it is, to my mind, one of the most important discoveries a human being has ever made. Now let me push on this a bit, because I want you to feel it in your own body, not just understand it as an idea. What does it actually mean to feel motion? What is happening in your muscles, your nerves, your inner ear when you say, I am moving? Think about riding in a car. You start at a red light. The light turns green. The driver hits the gas. What do you feel? You feel yourself pressed back into the seat. Your head tips backward. Something pushes on your whole body. That feeling is real. That feeling is acceleration, a change in speed. Now the car reaches cruising speed, 60 miles per hour on a smooth highway, straight road, flat terrain, no bumps. What do you feel now? Close your eyes and take stock of your body. What information are your senses giving you? Almost nothing. You feel the vibration of the engine maybe, the road noise, the hum of the tires. But those are not telling you about motion. Those are telling you about an engine running and rubber on asphalt. Take away those incidental sounds and vibrations. Make the ride perfectly smooth and quiet, and you feel precisely zero motion. You could be parked. You could be going 200 miles per hour. With your eyes closed and the ride smooth, your body cannot tell the difference. But then the driver slams the brakes. You fly forward against the seatbelt. You feel that immediately. The driver swerves around a pothole. You lean sideways. You feel that. The car accelerates to pass a truck. You press back into the seat. You feel that. You see the pattern? You do not feel velocity. You feel changes in velocity. Speeding up, slowing down, changing direction. Those are all forms of acceleration. And that is the thing your body detects. Your inner ear is the key instrument. You have 3 semicircular canals in each ear filled with fluid. When your head accelerates, the fluid resists the change and sloshes against tiny hair cells. Those cells fire signals to your brain. We are turning. We are tipping. Something has changed. But when the motion is steady, when you are cruising in a straight line at constant speed, the fluid moves with your head. No sloshing, no signal, silence. Your inner ear reports, nothing is happening. And here is the thing that really matters. This is not a defect. This is not evolution cutting corners. Your body is telling you the truth about physics. Constant velocity genuinely does not produce any force. There is no force to detect. If your inner ear reported constant velocity, it would be lying, inventing a signal where no physical phenomenon exists. Your body is honest. Embarrassingly honest. It tells you exactly what the laws of motion say. Acceleration is real, velocity is relative, and constant motion in a straight line is physically identical to rest. You are an acceleration detector, not a velocity detector. That distinction is the key to everything. Think about flying in an airplane, 35,000 feet, 550 miles per hour. The seatbelt sign turns off. You stand up. You walk down the aisle. You walk toward the back of the plane. Do you brace yourself against some invisible force? No. You walk as naturally as you would in your living room. You walk toward the front. You do not lurch forward as the plane's speed adds to your steps. It just feels like walking. The flight attendant pours orange juice into a cup. Does the juice fly sideways because the plane is tearing through the air at 500 miles per hour? Does it puddle toward the back of the cup? No. It pours straight down, sits level, behaves exactly like it would in a kitchen on solid ground. You are inside Galileo's ship. The airplane is the ship. The cabin is the sealed room. You, the juice, the cup, the air inside the cabin, all of you are moving forward at 550 miles per hour, and because you all share that velocity, it vanishes, it becomes invisible. Not approximately invisible, exactly invisible. You could run every physics experiment in the textbook inside that airplane cabin, and none of them, not one, would tell you whether you were moving or sitting on the ground with the engines off. Trains give you the same lesson, sometimes even more vividly. Have you ever been sitting in a train at a station, looking out the window at another train on the next track? The other train starts to move, and for a disorienting moment you cannot tell whether you are moving or the other train is moving. Your eyes say motion is happening, but they cannot assign it. Are you sliding backward, or is the other train sliding forward? You genuinely do not know until you look at the platform, or feel a jolt, or see some fixed reference point. That confusion is not a failure of your brain, it is a success of physics. The elevator is speeding up, and your body knows it instantly. Then the acceleration stops, and you are rising at constant speed, and you feel normal again. Perfectly normal. You cannot tell you are moving up. Then the elevator decelerates. You feel lighter for a moment. Your stomach floats slightly, and then it stops and you are still again. The elevator gives you the whole lesson in 30 seconds. Acceleration, you feel it. Constant velocity, invisible. Deceleration, you feel it. Stillness, indistinguishable from constant velocity. Your body is a beautiful, finely tuned instrument, but it is tuned to detect one thing and one thing only: changes in motion. Not motion itself. Changes, and if nothing changes, if the velocity is rock steady, your body reports perfect stillness, even at 1,000 miles per hour, even at 1,000,000. Now, apply all of this to the Earth. The Earth is the ship, the atmosphere is the cabin. Everything you interact with, the air, the oceans, the mountains, every molecule, all of it spins with the Earth. Shared velocity, invisible velocity. Same principle, same result. Now, people sometimes say, but wait, the atmosphere is not sealed, there is no cabin wall, why doesn't the air fly off, or at least lag behind? And the answer is gravity. The atmosphere is held to the Earth by gravity, just like you are. And the atmosphere rotates with the Earth because it has been doing so for billions of years. The air had plenty of time to spin up to speed. Friction between the ground and the lowest layers of air, and between each layer of air and the one above it, dragged the entire atmosphere into co-rotation long ago. The air is not being left behind any more than the ocean is being left behind or the mountains are being left behind. It is all on the same ride. It has been on the same ride since the Earth formed. This is different from sticking your head out of a car window. In that case, the air outside the car is not moving with the car. The car is plowing through stationary air, and you feel the result as wind. But on Earth, the air is not stationary. The air is spinning at the same speed as the ground. There is no relative motion between you and the atmosphere, just as there is no relative motion between you and the floor. So there is no wind, no drag, no sensation. That is the answer, and if that were the end of the story, it would already be profound. But it is not the end, because I snuck something past you, and the sharp ones in the audience have already caught it. Galileo's ship goes in a straight line, constant speed, constant direction. The principle of relativity applies perfectly and absolutely to straight-line, constant velocity motion. Physicists call this an inertial reference frame. The Earth is not going in a straight line. The Earth is spinning. Spinning means every point on the surface is traveling in a circle. And a circle is not a straight line. In a circle, you are constantly changing direction. Even if your speed stays the same, your direction is shifting at every moment. And a change in direction is an acceleration. So the surface of the Earth is accelerating centripetally toward the axis of rotation. And acceleration, we just established, is the thing you can feel. Your inner ear detects it, your body registers it. It is not invisible the way constant velocity is. So I seem to have a contradiction. I told you the motion is invisible, but now I am telling you there is an acceleration that should be detectable. Have I been lying to you? No. But I have been saving the punchline, because the resolution is not that the acceleration is zero, it is that the acceleration is laughably, absurdly, vanishingly small. Let us do the arithmetic. Centripetal acceleration equals the square of your velocity divided by the radius of the circle. At the equator, your speed from the spin is about 465 meters per second. The radius of the Earth is about 6.4 million meters. 465 squared is about 216,000. Divide by 6.4 million. You get roughly 0.034 meters per second squared. That number means nothing until you compare it to something, so compare it to gravity. The gravitational acceleration at the Earth's surface is 9.8 meters per second squared. That is the acceleration that pins you to your chair, that makes your coffee stay in the cup, that makes the ball fall when you drop it. The spin acceleration is 0.034. Gravity is 9.8. The ratio is about 1 to 288. The spin acceleration is 1/300th of gravity, about 1/3 of 1%. In human terms, if you weigh 150 pounds at the North Pole, where there is no spin effect because you are right on the axis, then at the equator the spin reduces your apparent weight by about half a pound. That is the weight of a couple of sticks of butter out of 150 pounds. Your bathroom scale cannot reliably distinguish that. Your body, with all its jiggly blood and shifting weight and breathing and heartbeat, has absolutely no chance. Now let me make the comparison even more vivid. You know what a merry-go-round feels like? A playground merry-go-round, the kind kids push and then jump on. It has maybe a 6-foot radius. If it is spinning once every couple of seconds, you can really feel the pull. You lean outward, you grip the bars. The centripetal acceleration is obvious, maybe 1 or 2 times gravity. The Earth has a radius of about 21 million feet, and it takes 24 hours to spin once, not 2 seconds. The radius is millions of times larger, and the rotation is tens of thousands of times slower. The centripetal acceleration shrinks with larger radius and shrinks with slower rotation. On the Earth-sized merry-go-round, the pull is not just small, it is a rounding error. It is noise. It is less than the acceleration you experience when you shift your weight from one foot to the other. What if the Earth spun faster? That is a fun question. If the Earth rotated once every 90 minutes instead of once every 24 hours, like the International Space Station orbits, the centripetal acceleration at the equator would be enormous. Objects would be noticeably lighter at the equator. Go fast enough, and things would fly off the surface entirely. The spin speed at which that happens, where centripetal acceleration equals gravity and your weight drops to zero, corresponds to a rotation period of about 84 minutes. At that speed, you would be weightless at the equator. A little faster, and you would be flung into space. Think about what that world would look like. People living at the poles would weigh normal. People at the equator would be almost floating. Jump off a chair in Ecuador, and you would drift down like an astronaut on the moon. The oceans would migrate toward the equator, piled up by the centrifugal effect, leaving the poles dry. The atmosphere would thin out at high latitudes and fatten at the equator. The planet itself would distort, bulging dramatically at the middle like a spinning ball of clay, and every freely moving object would curve wildly due to the Coriolis effect. Walking in a straight line would be nearly impossible, as the ground would constantly rotate under your feet during each step. You would need to lean into the rotation like a bicyclist leaning into a turn just to walk to the kitchen. It would be a completely different world, unrecognizable. We do not live on that world, thankfully. We live on a planet where the rotation is so sluggish, by the standards of spinning objects, that the centripetal effect is a footnote, 1 revolution per day. Compare that to a kitchen blender at 20,000 revolutions per minute, or a hard drive platter at 7,200 revolutions per minute, or even a lazily spinning basketball on your finger at maybe 3 revolutions per second. The Earth does 1 revolution per day. It is, by any standard, barely rotating at all. And that lethargy, combined with the enormous radius, crushes the centripetal effect down to a rounding error. So the real answer has 2 layers, and both are essential. Layer 1, constant velocity. Straight line motion produces exactly 0 detectable effect. This is not practical. It is fundamental. It is a law of physics, as firm as the conservation of energy. No instrument, no matter how sensitive, can detect pure uniform motion. There is nothing to detect. Layer 2, the Earth's rotation adds a tiny centripetal acceleration that is, in principle, detectable, but it is 1/300th of gravity, and your body has no chance of noticing it. It takes special instruments and very clever experiments. Together, those 2 layers explain the entire puzzle. you are sitting on a rocket and feeling nothing, because the velocity is shared and the acceleration is negligible. But if the acceleration is there, even if it is tiny, someone must have found a way to detect it. And the way they did it is one of the most beautiful demonstrations in the history of experimental physics. Paris, 1851. A French physicist named Léon Foucault. He went to the Pantheon, one of the grandest buildings in the city, with a cavernous dome rising over 200 feet, and he hung a pendulum from the top of that dome. This was not a delicate tabletop toy. The wire was about 220 feet long. The bob was a heavy iron sphere, roughly 60 pounds, polished to a sheen, with a small stylus attached to the bottom so it could trace its path through a ring of sand on the floor. He pulled the bob to one side, tied it in place with a thin cotton thread, and then burned the thread with a candle, releasing the pendulum with no push, no twist, no sideways impulse at all. Clean, pure, a perfect start. The pendulum began to swing, back and forth, a slow, majestic arc, each oscillation taking several seconds because of the enormous length of the wire. Nothing but gravity and inertia at work, the simplest motion in physics. Important people had gathered to watch. Scientists, politicians, journalists. They stood around the sand ring on the floor, and at first the demonstration seemed almost boring. A pendulum swinging. So what? Pendulums had been swinging for centuries. Then Foucault and the spectators waited, and over the course of the first hour something eerie became visible. The stylus at the bottom of the bob was tracing its line through the sand, and the line was slowly shifting. The plane of the pendulum's swing was rotating, clockwise, as viewed from above, at about 11 degrees per hour in Paris. The pendulum was knocking down little pegs placed around the sand circle, one after another, as the plane of the swing swept past them. Nobody touched it, nobody blew on it. The pendulum was doing exactly what Newton's laws say a swinging weight should do. It was oscillating back and forth in a fixed plane, fixed not relative to the floor but relative to the distant stars. The pendulum has no connection to the earth. It does not care that it is hanging from a Parisian building. It swings back and forth in absolute space, governed by inertia and gravity and nothing else. But the floor of the Pantheon does care. The floor is bolted to the earth. The earth rotates. And as the hours pass, the floor and the building and the spectators and all of Paris slowly rotates underneath the pendulum. The pendulum appears to drift, but it is not drifting. It is the most honest object in the room. It is the floor that is moving. If you took the pendulum to the North Pole, the floor would rotate all the way around under it in 24 hours, 15 degrees per hour, a full circle in a day. At the equator, the effect vanishes because the axis of rotation is parallel to the floor. At intermediate latitudes, you get intermediate rates. The mathematics predicts exactly how fast the plane should process at any latitude, and when Foucault measured it in Paris, the observation matched the prediction perfectly. You can go see Foucault pendulums today. They hang in science museums around the world. You walk into the hall, you look at the pendulum swinging, and you watch the peg markers on the floor get knocked down one by one as the plane of the swing slowly rotates. You are watching the earth rotate, live, with your own eyes, using nothing but a weight and a wire. I find something deeply moving about that. For thousands of years, people argued about whether the earth moves. And the proof, all along, was just a ball on a string, hanging there, telling the truth, while the whole world turned underneath it. There is another fingerprint of the rotation, and this one actually matters in everyday life, the Coriolis effect. Picture yourself at the North Pole. You have a cannon. You aim it due south and fire. The cannonball leaves the barrel and heads toward a target directly south of you. But while the ball is in the air, the earth rotates underneath it. The target, which was due south when you fired, slides a bit to the east during the flight time. When the ball arrives, the target is not where it was. From your perspective on the rotating ground, the cannonball appears to have curved to the right. You aimed true, it missed, but the ball did not curve. The ball flew in a perfectly straight line through space. The ground moved, the target wandered away. The curve is an illusion caused by observing straight-line motion from a rotating platform. In the northern hemisphere, this effect deflects moving objects to the right, in the southern hemisphere to the left, and the consequences are spectacular. Hurricanes. Here is what happens. A patch of ocean heats up, warm moist air starts rising, surrounding air rushes in to fill the void. If the earth were not spinning, the air would converge straight inward, pile up and dissipate, storm over. but the Earth is spinning, and the Coriolis effect bends the inflowing air sideways. In the northern hemisphere, the deflection is to the right, which means air trying to rush inward gets turned counterclockwise. It cannot reach the center directly. It spirals around it, faster and faster, tightening into that terrifying pinwheel you see in satellite images. The entire structure of a hurricane, that beautiful lethal spiral, is a direct consequence of living on a spinning planet. In the southern hemisphere, the deflection reverses, and the spiral goes clockwise. This is not legend. This is not folklore. Every tropical cyclone on Earth has its rotation stamped on it by the Coriolis effect. People sometimes ask about bathtub drains. Does the water spiral one way in the northern hemisphere and the other way south of the equator? The answer is in theory yes. In practice, no. The Coriolis effect is proportional to the scale and speed of the moving object. For a bathtub, the effect is absurdly tiny, overwhelmed by the shape of the basin, the direction you pulled the plug, residual currents in the water, and a dozen other factors. You cannot see the Earth's rotation in a draining bathtub. You need large-scale, long-duration motion like weather systems for the Coriolis force to dominate. But on those large scales, it is unmistakable. Ocean currents are bent by it. Trade winds are shaped by it. During the First World War, German engineers built a gun called the Paris gun that hurled shells over 75 miles. The shells were in flight for several minutes, arcing high into the stratosphere. At that range and that duration, the Coriolis deflection moved the impact point noticeably. The gunners had to aim off target, compensating for the fact that Paris was going to slide sideways while the shell was in the air. The rotation of the Earth, invisible to your morning routine, computable by an artillery officer. So the spin is not truly invisible. It is quiet. In everyday life, in your kitchen, in your car, it produces nothing you can detect. But if you are patient or precise, or if you look at large enough systems, the rotation shows its hand. All right? But here is what I have been saving, because everything I have told you so far is the answer to the question, and the answer is good, but it is not the whole story. The whole story is stranger. See, there is a follow-up question that most people never think to ask. You cannot feel the Earth spinning. Fine. But what if you could not feel any motion at all? What if there were no way, even with perfect instruments and unlimited cleverness, to determine how fast you are really going? What if the phrase "how fast you are really going" does not even mean anything? That sounds absurd, but it is the truth, and it rewrites everything. The question, "Why can't I feel the Earth spinning?" seems like a question about the Earth. It is not. It is a question about the nature of motion. And the answer leads to one of the most radical ideas human beings have ever confronted. There is no such thing as absolute motion. I want you to sit with that for a moment, because people hear it, nod, and then continue thinking exactly the way they thought before. There is no experiment, not even in principle, not with any conceivable technology, that can tell you your absolute velocity through space. This is not because we have not tried hard enough. This is not because the instruments are not sensitive enough. The concept itself is empty. It refers to nothing. There is no motionless in the universe. There is no cosmic background grid painted on space against which you can measure your speed. Velocity is a relationship between two objects. Always. Without exception. You can say the Earth moves at 1,000 miles per hour relative to its own axis. You can say it moves at 67,000 miles per hour relative to the Sun. You can say it moves at 500,000 miles per hour relative to the galactic center. You can say it moves at 1.3 million miles per hour relative to the cosmic microwave background. And every single one of those numbers is correct. But none of them is the real speed. There is no gold standard. There is no privileged frame. Every velocity is equally valid, because velocity simply does not exist as a standalone property of an object. It is always a comparison. Think of it this way. Saying I am moving at 67,000 miles per hour, without specifying relative to what is like saying I am north. North of what? You cannot be just north. North is a relationship between 2 points. You are north of Mexico. You are south of Canada. You are not just north in some absolute cosmic sense. The word requires a reference. Velocity is the same. You need two things. Without two things, the concept evaporates. From your own point of view, sitting in your chair, your velocity is zero. You are at rest. And that is not a convenient approximation. That is rigorous, legitimate, correct physics. Your reference frame is exactly as valid as anyone else's. A physicist on a spaceship, going 90% of the speed of light relative to you, would say she is at rest and you are the one moving at 90% of the speed of light. and she would be exactly as correct as you are. Neither of you has a better claim to being really stationary. People push back on this. They say, but the Earth is really spinning. We proved it with the pendulum, and yes. Rotation is special. Rotation involves acceleration, and acceleration is absolute. The Foucault pendulum detects rotation without looking at the stars. The Coriolis effect detects rotation without any external reference. You can distinguish a rotating frame from a non-rotating frame using local experiments. That is a real distinction. But straight-line constant speed motion, that is purely, totally, irreducibly relative. The Earth's orbit around the Sun's orbit around the galaxy's flight through the cosmos. Over short timescales, these are all essentially straight lines at constant speed. The curves are so gentle, the radii so enormous, that the accelerations are even tinier than the spin acceleration. The orbital acceleration of Earth around the Sun is about 6/1000ths of a meter per second squared, roughly 5 times smaller than the spin acceleration. The galactic acceleration is smaller still. These motions are, for all practical and most theoretical purposes, undetectable. This is why you cannot feel any of the big velocities, not the orbit, not the galactic drift, not the cosmic motion. They are all straight-line motion in disguise, and straight-line motion at constant speed produces exactly zero physical effect. Not approximately zero, exactly zero. This is a theorem, not an observation, and people tested it. In 1887, 2 American physicists, Albert Michelson and Edward Morley, built one of the most precise optical instruments of their era. They were trying to measure the Earth's velocity through the supposed luminiferous ether, the hypothetical medium that everyone assumed light needed to travel through, the way sound needs air. Their idea was elegant. If the Earth is plowing through the ether as it orbits the Sun, then a beam of light traveling in the direction of the Earth's motion should move at a slightly different speed than a beam traveling perpendicular to it. It is the same logic as swimming with the current versus across the current. Measure both speeds precisely, compare them, and you have detected absolute motion through the ether. They measured, they compared, and they found nothing. Zero difference. No matter which direction they pointed their apparatus, no matter what time of year, no matter how they refined their instruments, the speed of light was the same in every direction. The ether was not there. The absolute motion was not there. Michelson called it a failure. It was one of the most successful experiments in history. It proved that you cannot detect uniform motion, period. Not mechanically, not optically, not by any means at all. The principle of relativity holds even for light. Galileo realized this in 1632. Newton baked it into his laws of motion. And then, around 1905, a young patent clerk in Bern, Switzerland, took the idea and pushed it to its absolute limit. Albert Einstein asked a question that sounds simple and is anything but. If the laws of mechanics are the same in all inertial reference frames as Galileo said, what about the laws of electromagnetism? What about light? Maxwell's equations, which describe electricity, magnetism, and light, predict that electromagnetic waves travel at a definite speed, about 186,000 miles per second. But relative to what? If you are on a train going half the speed of light, and you turn on a flashlight, does the light zoom ahead of you at 1.5 times its usual speed? Newtonian common sense says yes. You add velocities. My speed plus the light speed gives the total. But Maxwell's equations say something troubling. They predict a fixed speed with no mention of any reference frame. The speed of light just is what it is. It does not say relative to the ground or relative to the source or relative to anything, just this fast. Period. Einstein took that at face value. He said the speed of light is the same in every inertial reference frame. You cannot outrun it. You cannot boost it. You cannot subtract from it. No matter how fast you are going, when you measure the speed of a beam of light, you get the same answer. And that single assumption, combined with Galilean relativity, blows the entire framework of space and time apart. If the speed of light is the same for everyone, then time must behave differently for different observers. Moving clocks run slower. Moving rulers shrink. Events that happen simultaneously for one person do not happen simultaneously for another. And the most famous equation in physics falls out. Energy equals mass times the speed of light squared. Think about how shocking this is. Galileo in 1632 said you cannot feel uniform motion inside a sealed cabin. A perfectly reasonable, almost obvious observation. 300 years later, Einstein takes that same principle, applies it with total logical rigor to light, and discovers that time is not universal, that space is not rigid, that a clock on a fast-moving spaceship ticks slower than an identical clock on the ground, that a meter stick carried at high speed is physically shorter than one at rest. These are not illusions, these are not measurement errors, these are real physical consequences of the fact that you cannot distinguish between rest and uniform motion. The same principle that makes your coffee sit still on a spinning planet also makes time flexible and space elastic. One idea, from a boat in 1632 to the reshaping of the cosmos in 1905, the longest, most productive thread in the history of physics, the entirety of special relativity, time dilation, length contraction, mass-energy equivalence, the geometry of space-time itself, all of it traces back to this one quiet starting point. You cannot feel constant motion. And the physics inside a moving room is identical to the physics in a room at rest. Galileo's ship, the airplane cabin, your coffee cup on a spinning earth. Pull the thread of a child's question, and you unravel 4 centuries of physics. Let me close with an image, because I want this to stay with you, not as a fact you memorize, but as a feeling you cannot shake. You are lying on your back in an open field at night. The air is still. The grass is cool against your shoulders. The sky is clear and the stars are burning white. You feel the weight of your body pressing into the earth. Stillness everywhere. Perfect, absolute stillness. And then over the hours, the sky begins to move. Slowly, silently, the whole dome of stars rotates. Orion is over there at 9 in the evening. By midnight, he has shifted. By 3 in the morning, he has crossed half the sky. The entire canopy of the heavens is turning around a point near Polaris. One full revolution every 24 hours. Your senses tell you a simple story. You are still. The sky is turning. And this is the story every civilization told for thousands of years. The Egyptians, the Greeks, the Chinese, the Maya. They all looked up and saw the same thing. A revolving sky around a stationary earth. It is the most natural reading. The most intuitive interpretation. The ground is solid and fixed. The heavens are in motion. And it is perfectly backwards. The stars are still. You are spinning. The planet beneath your back is a vast turntable, rotating at 1,000 miles per hour, carrying you in an enormous circle. The stars barely move at all relative to each other on the time scale of a single night. It is the ground that rotates. It is your vantage point that sweeps through the sky. And the only reason you interpret it the other way around is that your senses report local conditions. Inside your local bubble, everything is still, because everything in the bubble shares your motion. The air above you is spinning with you. The grass beneath you is spinning with you. Every molecule you can interact with is on the same ride. So from inside the bubble, the motion is invisible. And you project that local stillness outward onto the whole universe and conclude that you are the fixed point and the sky is moving. This is the oldest illusion in science, and it persisted for millennia. Not because people were foolish, but because the physics is genuinely rigorously designed to make uniform motion undetectable. People did not fail to notice the spin. The spin was hidden by the architecture of the universe itself. Galileo caught the lie in 1632. Newton explained exactly how the truth works. Foucault proved it with a ball on a string in 1851, making the Earth's rotation visible in a marble hall without a single window to the sky. And Einstein, taking the principle of relativity as far as it could go, showed that the very concepts of time and distance bend and flex depending on how you are moving. All of it starts here, with the fact that you are hurtling through space at 1,000,000 miles per hour, and your coffee is still. The ride is smooth, impossibly smooth. The smoothness is not an accident. It is not engineering, it is physics. It is the deep geometry of space and time, arranged so that shared motion, no matter how fast, no matter how violent, is always perfectly silent. And here is the thing that keeps me up at night, in the good way. A 6-year-old asks, "How come I can't feel the earth moving?" And the adults in the room chuckle and say, "Good question," and change the subject, because they do not know the answer. They think they should know the answer because the question sounds simple. But the question is not simple, it is a depth charge. It goes through Galileo, through Newton, through the deepest structure of what motion means, and it lands at the feet of Einstein. One child's question. 4 centuries of physics, and the answer redefines space and time. That is how science works. The simple questions are never simple. They are the trapdoors. Step on them, and you fall into the architecture of nature. So I want you to take this with you. The next time you are outside at night, watching the stars arc across the sky, remember, the sky is the honest one. The sky is holding still. It is the ground that is lying, and you cannot feel the lie because the lie is shared by everything you are made of. Now tell me something. Does the ground feel any different? Right now, knowing what you know, does sitting still feel a little less certain? When you look up at the stars tonight, will you remember that it is the floor that turns and the sky that holds steady? I hope so, because that tiny inversion, that moment when the solid earth becomes the moving thing and the distant stars become the fixed frame, that is what physics feels like when it really gets under your skin. And once it is in there, it does not leave.